What if I told you something out there, something massive and invisible, is dragging our entire galaxy toward it at an incomprehensible speed of 14 million miles per hour? Picture this: the Milky Way, with its hundreds of billions of stars, isn't just drifting aimlessly through space. It's being pulled, almost yanked, toward a cosmic mystery so profound it challenges everything we think we know about the universe. This force has a name, the Great Attractor, and it's not alone. Surrounding it are vast, enigmatic structures, colossal filaments of galaxies, immense voids, and dark matter weaving the fabric of reality itself. These aren't just distant curiosities, they're the hidden architects of our cosmic fate. For decades, astronomers have been piecing together clues about this gravitational anomaly, but the more we learn, the more questions arise. How can something so powerful remain nearly invisible to our telescopes? What secrets lurk in the shadows of these gigantic cosmic webs? And perhaps the most haunting question of all, if the Great Attractor is pulling us, what else is out there waiting to be discovered? The answers could rewrite the story of the universe and our place within it. That's exactly what we're diving into today. Over the next 30 revelations, we'll unravel the mysteries of the Great Attractor and the large-scale structures that shape our cosmos. From the mind-bending scale of galaxy superclusters to the eerie influence of dark energy, each secret pulls back another layer of this grand celestial puzzle. And here's the thing, you don't need a degree in astrophysics to come along for the ride. We'll walk through these concepts together, blending awe-inspiring science with the thrill of exploration. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. The Great Attractor hides in plain sight, or rather, it would if our own galaxy didn't stand directly in the way. Imagine trying to peer through a dense fog while standing in the middle of it. That's essentially the challenge astronomers faced when they first detected this gargantuan gravitational force. The culprit, a region of space called the Zone of Avoidance, a stretch of sky where the Milky Way's thick clouds of gas, dust, and stars block our view like a cosmic blindfold. For centuries, telescopes pointed toward this zone saw little more than darkness, leaving scientists to wonder, what was pulling entire galaxies, including ours, with such irresistible force? The breakthrough came when technology caught up to the mystery. Traditional optical telescopes were useless here. Their light couldn't penetrate the Milky Way's dusty veil. But infrared and radio telescopes changed everything. These instruments don't rely on visible light. They detect the heat signatures of objects or the radio waves they emit, slicing through obstructions like an X-ray. When astronomers aimed them toward the Zone of Avoidance, the Great Attractor's rough location snapped into focus. Roughly 250 million light-years away, nestled within the Laniakea Supercluster, a mind-bending web of galaxies spanning over 500 million light-years. But here's the twist: even now, we can't see the Great Attractor directly. Its gravity betrays its presence, warping the paths of galaxies around it, yet its core remains shrouded. Some theories suggest it's not a single massive object, but a dense knot of galaxies and dark matter, a gravitational nexus where the universe's invisible scaffolding converges. Others propose even wilder ideas, like a confluence of dark energy or a ripple in spacetime itself. One thing's certain: the more we uncover, the more the Great Attractor defies simple explanation, reminding us that the cosmos always keeps its deepest secrets just out of reach. But the Great Attractor isn't the only heavyweight in this cosmic wrestling match. Lurking even farther away, some 650 million light-years from Earth, lies a contender so massive it could rewrite the rules of our galactic motion. Meet the Shapley Supercluster, a sprawling metropolis of galaxies so dense and powerful that its gravity might actually be winning the tug-of-war against the Great Attractor. With over 8,000 galaxies packed into its expanse, Shapley's gravitational pull is like a siren song, so intense that some researchers argue it, not the Great Attractor, is the true puppeteer behind our galaxy's relentless journey through the cosmos. Here's where things get fascinating. The Milky Way isn't just being pulled toward one of these behemoths, it's caught in the crossfire of their competing forces. Imagine two giants playing a game of cosmic tug-of-war with our galaxy as the rope. The Great Attractor tugs us inward, but Shapley's sheer size and distance give it a surprising advantage. Its gravitational influence stretches across unfathomable distances, subtly altering the trajectories of entire galaxy clusters, including our own. Some simulations even suggest that up to half of our observed motion could be due to Shapley's far-reaching grasp. So why isn't Shapley more famous? For one, it's incredibly far away, so distant that its light began traveling toward us when Earth's continents were still clumping together in the Precambrian era. But more importantly, its story challenges a fundamental assumption that the closest massive object must dominate our motion. Shapley proves that gravity doesn't care about proximity alone. Mass and density are the real dictators of cosmic influence. Think of it like this: if the Great Attractor is a nearby magnet, Shapley is an entire magnet factory, its collective pull outweighing its rivals despite the extra distance. Yet the debate isn't settled. Some astronomers point out that Shapley's sheer scale makes its influence harder to pin down precisely. Others speculate that undiscovered structures could be adding their own invisible tugs to the mix. What's clear is this: our galaxy's path isn't dictated by a single force, but by an intricate dance of gravity's heaviest players, a reminder that the universe loves a good plot twist. And as telescopes grow more powerful, we might soon discover that even Shapley is just one piece of a puzzle spanning billions of light years. Now, let's venture into one of the most baffling mysteries tied to the Great Attractor, one that challenges our understanding of the cosmos itself. It's called dark flow, and it's exactly as eerie as it sounds. Picture this: not just our galaxy, but hundreds of galaxy clusters are all streaming in the same direction at staggering speeds of nearly 1,000 kilometers per second, as if some unseen hand is herding them toward something. But here's the kicker: there's no visible source of gravity powerful enough to explain this motion. No supercluster, no Great Attractor, nothing we've detected so far can account for it. So what's really going on? When astronomers first noticed dark flow in the early 2000s, it sent shockwaves through the scientific community. The discovery came from studying the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature shifts in this ancient light revealed something startling. Entire galaxy clusters were moving beyond the pull of known cosmic structures, as if lured by something outside our observable universe. That's right, this isn't just about the Great Attractor anymore. Dark flow hints at forces so vast they might originate from regions of space we can't even see beyond the cosmic horizon. But not everyone's convinced. Skeptics argue that dark flow could be a measurement error, or perhaps the gravitational echo of colossal structures we simply haven't mapped yet, like an even more massive sibling of the Shapley Supercluster lurking in the darkness. Others propose something far wilder, that our universe is being tugged by the gravity of a neighboring universe, a parallel cosmos brushing against our own like ships passing in the night. Imagine that the ultimate cosmic conspiracy, where our fate is tied to realms we might never observe directly. The debate rages on, but one thing's clear: dark flow forces us to rethink the limits of our cosmic neighborhood. If the Great Attractor is a mystery, dark flow is a full-blown enigma, a cosmic breadcrumb trail leading to questions we're only beginning to ask. And as our telescopes peer deeper into the void, who knows what invisible giants we'll find steering the universe's grand dance. Think of the universe as a colossal river system where galaxies aren't just floating, they're flowing. And in 2014, astronomers made a jaw-dropping announcement: our Milky Way isn't some isolated island in space. It's a tiny neighborhood in an almost unimaginably vast metropolis called the Laniakea Supercluster, a sprawling cosmic watershed 500 million light-years wide. Picture 100,000 galaxies, including our own, all drifting together like leaves caught in the same gravitational current. This wasn't just a new label, it was a complete redefinition of our cosmic address. What does it mean to live in a supercluster? Imagine gravity as the invisible hand sculpting the universe's grandest structures. Laniakea Hawaiian for immeasurable heaven isn't a random clump of galaxies. It's a delicate web of filaments, with galaxies streaming toward denser regions like rivers merging into a mighty delta. At its heart lies the Great Attractor, the gravitational anchor pulling everything inward. But here's the twist: Laniakea isn't a fixed shape. It's a dynamic, ever-shifting network where galaxies move in slow-motion cascades, tracing the contours of dark matter we can't even see. The discovery hinged on a revolutionary way of mapping cosmic motion. Instead of just measuring distances, scientists tracked the subtle velocities of galaxies, how they're tugged by gravity's unseen tides. This revealed something extraordinary. The Milky Way isn't just near the Great Attractor. We're part of its vast watershed, one tributary in a river of galaxies flowing toward the same cosmic drain. And Laniakea has rivals. Nearby superclusters like Perseus Pisces form their own watersheds, creating a universe where gravity carves borders as real as continental divides on Earth. Yet this reclassification comes with a humbling reality check. On Laniakea's scale, even a galaxy as majestic as ours feels like a speck of dust in a swirling storm. It's a reminder that the universe operates on levels far beyond human intuition, where nearby means hundreds of millions of light years, and home is just a fleeting snapshot in an endless river of stars. The Great Attractor's gravitational grip is so intense that it defies explanation, because when astronomers tally up all the visible matter in its vicinity, the numbers just don't add up. Think of it like hearing thunder so loud it shakes your windows, but when you look outside, there's not a cloud in sight. That's the puzzle here. The Great Attractor's gravity behaves as if it's packing the mass of 10 quadrillion suns, yet the galaxies we can actually see in its neighborhood account for only a fraction of that heft. To put that in perspective, our Milky Way, with its 1.5 trillion solar masses, is practically a featherweight in comparison. So where's all that missing mass coming from? This discrepancy points to one of cosmology's greatest enigmas: dark matter. Imagine the Great Attractor as a cosmic iceberg, with the galaxies we observe as just the tip peeking above the surface. Beneath lies an invisible scaffolding of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, yet exerts gravitational pull like ordinary matter. Scientists estimate that dark matter outweighs visible matter by a factor of 5 to 1, meaning the Great Attractor's true power comes not from the glittering galaxies we see, but from this shadowy framework weaving through space. But here's where things get even stranger. Even when we account for dark matter, some researchers argue the Great Attractor's influence might still be stronger than expected. Could there be another layer to this mystery? Some speculate that vast, undiscovered reservoirs of dark matter, clustered in ways we don't yet understand, are amplifying its pull. Others wonder if the attractor sits at a crossroads of cosmic filaments, where dark matter flows converge like rivers feeding a lake, creating a gravitational hotspot. What's undeniable is how this invisible hand shapes our galactic journey. The Milky Way's motion isn't just a leisurely drift, it's a headlong rush into the unknown, steered by forces we're only beginning to map. And as astronomers refine their models, one truth becomes clear: the universe holds its cards close, revealing just enough to keep us chasing the shadows. The universe doesn't just scatter galaxies randomly, it organizes them along sprawling, invisible highways of dark matter, threading through the cosmos like a colossal spider's web. And right where these filaments intersect, you'll find the Great Attractor, perched like a gravitational toll booth at the crossroads of the cosmic expressway. Picture this: thin, tendril-like structures of dark matter stretch for billions of light years, connecting galaxy clusters in a delicate lattice. Galaxies don't just float through empty space, they ride these filaments like commuters on a subway, funneled toward dense knots where the threads converge. That's how the Great Attractor got its pull. It's not just a massive object, it's a hub where the universe's hidden infrastructure meets. Simulations of this cosmic web look almost organic, like watching neurons fire in a brain or roots spreading through soil. Supercomputers crunching the data reveal something astonishing. Galaxies move faster along these filaments, as if space itself has built-in gravitational currents. Instead of drifting aimlessly, they're funneled efficiently toward superclusters, picking up speed as they approach intersections like the Great Attractor. Think of it like a river narrowing into rapids where the water, or in this case, galaxies, gains momentum as the channel tightens. But here's what's even wilder: these filaments aren't just passive roads. They're dynamic, evolving structures. As dark matter clumps and shifts over eons, the web's layout changes, rerouting galaxies onto new paths. Some researchers compare it to a living circulatory system, with dark matter as the blood and galaxies as the cells being shuttled along. And just like a city's growth depends on its highways, the Great Attractor's dominance hinges on its place at the junction of multiple filaments, a cosmic grand central station with gravity as its timetable. Yet for all we've mapped, much of this web remains uncharted. The filaments themselves are nearly invisible, detectable only by how they warp the light of galaxies behind them or tug on stars passing by. It's like trying to trace the outline of a shadow in a pitch-black room. But with each new simulation and deeper sky survey, we're slowly sketching the blueprint of this hidden network, the true scaffolding of the universe where dark matter's silent highways dictate the fate of everything we see. If gravity pulls us toward the Great Attractor, why isn't our galaxy hurtling even faster through the cosmos? The answer lies in one of the universe's most counterintuitive phenomena, an enormous absence of matter pushing us away. Meet the dipole repeller, a cosmic void so staggeringly empty that its lack of gravity creates a repulsive force, acting like a mirror image to the Great Attractor's pull. Picture a desert spanning 460 million light-years, where galaxies are vanishingly rare, and the density of matter is a whisper compared to the universe's average. This isn't just empty space, it's a gravitational hill our galaxy is rolling away from, as if the universe itself is pressing us toward richer cosmic neighborhoods. Here's how it works. While the Great Attractor tugs us inward with its concentrated mass, the dipole repeller's emptiness creates a relative lack of gravitational pull. In the grand equation of cosmic motion, this imbalance functions like a push. Imagine standing between two friends, one grabbing your hand while the other lets go. You'd naturally lean toward the one holding on, not because the other pushed you, but because their absence of force made the first grip dominant. That's the dipole repeller's role. Its void doesn't emit some anti-gravity. Instead, the surrounding denser regions like the Great Attractor exert comparatively stronger pulls, making us effectively recoil from the emptiness. The discovery of this void rewrote our understanding of large-scale flows. For decades, astronomers struggled to explain why the Milky Way's motion didn't perfectly align with the Great Attractor's position. Then, in 2017, researchers crunched the numbers and realized an eerie truth. Our path makes perfect sense only when accounting for both the attractor's pull and the repeller's push. It's a cosmic tug-of-war where one player isn't even holding the rope. They're just stepping back, altering the balance, but the dipole repeller isn't alone. Scattered across the universe are other vast voids like the Boötes void, a spherical emptiness spanning 330 million light-years, each playing its part in sculpting galactic motions. These regions aren't just passive gaps, they're active participants in the universe's structure, their absence shaping the paths of galaxies as surely as clusters do. And just like the Great Attractor, the repeller hides in plain sight, its presence inferred not by what's there but by what isn't. What's truly mind-bending is the scale of this push and pull. The dipole repeller lies roughly 700 million light-years behind us, while the Great Attractor sits 250 million light-years ahead. Between them, our galaxy is like a raft caught between two currents, one a rushing river, the other a still lagoon, with both forces fine-tuning our trajectory through the cosmos. And somewhere out there, other voids and attractors are doing the same to countless galaxies, weaving an intricate dance of presence and absence that dictates where everything is headed. Yet mysteries remain. Mapping these voids is like trying to trace the outline of a shadow. You can't see the emptiness itself, only how it bends the light of galaxies around it. Some scientists speculate that even larger, undiscovered voids could be lurking beyond our current maps, their repulsive influence still unaccounted for. Others wonder if dark energy, the enigmatic force accelerating the universe's expansion, might amplify these effects, turning cosmic deserts into gravitational repellers on an even grander scale. One thing's certain, the universe doesn't just move toward mass. Sometimes it's the lack of mass that sets everything in motion. Most galaxies obey a cosmic speed limit. The faster they move away from us, the farther they're located, a relationship so reliable it's called Hubble's law. But scattered across the universe are galactic outlaws like the supergiant elliptical galaxy NGC 4889, breaking every rule by racing far faster than their distance should allow. These cosmic speedsters don't just drift, they hurtle, as if some unseen force has given them an extra gravitational kick, and that's exactly what's happening. Their peculiar velocities, the term astronomers use for these unexpected motions, are cosmic breadcrumbs pointing straight toward the Great Attractor's hidden influence. Take NGC 4889, a monster lurking 650 million light-years away in the Coma cluster. By all rights, its immense distance should mean it's receding from us at a predictable speed, carried along by the universe's expansion. Instead, it's zipping through space with a peculiar velocity of over 3,000 kilometers per second, fast enough to cross the continental United States in less than a second. That's not cosmic expansion at work, it's something far more intriguing. This galaxy isn't just moving away from us, it's being pulled sideways by the colossal gravity of the Great Attractor and its surrounding supercluster web, like a ship caught in an invisible current. The real shocker, NGC 4889 isn't alone. From the Fornax cluster's sprinting galaxies to oddballs like Messier 87, these cosmic rebels share a pattern. They're all downstream from the Great Attractor's gravitational watershed. Imagine tossing confetti into a swirling drain. Most pieces flutter predictably, but a few get snagged by hidden eddies, their paths twisting unexpectedly. That's the effect we're seeing on an intergalactic scale. The Great Attractor's gravity warps local space-time, redirecting galaxies like a cosmic puppeteer tweaking strings we can't see. Yet the mystery deepens when we map these peculiar velocities across the sky. They converge toward the Great Attractor like compass needles pointing north, but some galaxies move too fast, faster than the attractor's known mass should allow. This discrepancy hints at something thrilling. We're still missing pieces of the puzzle. Could unseen dark matter clumps be amplifying the tug? Or is the Great Attractor itself more massive than our current maps suggest? Every rogue galaxy adds another clue, revealing how gravity's whispers echo across millions of light-years, rewriting the rules of motion in ways we're only beginning to decode. What makes these galactic anomalies so valuable isn't just their speed, it's their defiance. By refusing to follow Hubble's law, they expose the hidden scaffolding of our universe, proving that expansion isn't the only force shaping cosmic motion. They're living proof that gravity's reach extends far beyond what we can see, tying distant galaxies to the Great Attractor's shadowy domain. And as astronomers catalog more of these speedsters, one truth becomes clear. In the grand cosmic dance, even the outliers are following steps. We just haven't learned the whole routine yet. Buried behind the Milky Way's dusty heart, where most telescopes see only shadows, lies a secret metropolis of galaxies, one that could hold the key to the Great Attractor's immense power. This is the Norma Cluster, a bustling galactic city known to astronomers as ACO 3627, packed with hundreds of galaxies so close together their gravity tangles like a cosmic traffic jam. For centuries, this cluster was completely hidden from view, swallowed by the zone of avoidance. That same region where our galaxies bulge blocks our line of sight like a towering mountain range. But when researchers finally pierced the veil, they didn't just find a few stray galaxies, they stumbled upon a gravitational powerhouse actively feeding the Great Attractor's insatiable pull. The discovery hinged on a shift in perspective literally. Optical telescopes couldn't cut through the Milky Way's thick dust, but X-ray telescopes like NASA Chandra saw right through the obstacle. Why? Because the Norma Cluster isn't just a collection of galaxies. It's a cauldron of superheated gas reaching temperatures of 100 million degrees, glowing fiercely in X-rays. Imagine trying to spot a city at night through fog. Your eyes might fail, but infrared goggles would reveal its heat signatures blazing through the mist. That's exactly how X-ray astronomy exposed this hidden marvel. Suddenly, what appeared as an empty void became a radiant hub, its galaxies orbiting a shared center of gravity like bees around a hive. Here's what makes Norma Cluster so extraordinary. It's not just near the Great Attractor, it's practically its core. Gravitational models suggest this dense knot of matter contributes significantly to the attractor's pull, acting like a hidden anchor in the cosmic tug-of-war. Some astronomers even argue that Norma is the Great Attractor, or at least its beating heart, with surrounding superclusters like Laniakea amplifying its influence. Picture a massive concert where the lead singer Norma stands just offstage, their voice gravity booming through speakers' filaments of dark matter to reach every corner of the venue. But Norma isn't alone in this shadowy realm. Recent surveys have uncovered other hidden giants like the galaxy-rich Vela cluster, lurking in the zone of avoidance, each adding its weight to the Great Attractor's gravitational web. Together, they form a hidden skeleton of mass, explaining why our galaxy's motion defies simple calculations. It's as if we've been trying to solve a jigsaw puzzle with half the pieces flipped upside down, only now are we turning them over, revealing the full picture. Yet for all we've uncovered, the zone of avoidance still guards its secrets fiercely. Less than 20% of this region has been mapped in detail, leaving astronomers to wonder what else is hiding in our own backyard. Could there be even larger clusters or exotic structures unlike anything we've seen, waiting to reshape our understanding of the attractor's reach? One thing's certain: every time we peer behind the Milky Way's dusty curtain, the universe reminds us that its greatest mysteries aren't always in the distant cosmos. Sometimes they're right in front of us, hidden in plain sight. Just when we thought the Great Attractor was the only heavyweight lurking behind the Milky Way, astronomers unveiled a hidden rival, one that could rewrite our understanding of this cosmic tug-of-war. Meet the Vela Supercluster, a gargantuan structure stretching over 370 million light-years, concealed for eons by our galaxy's interstellar dust. Discovered in 2016 through painstaking analysis of thousands of galaxies' redshifts, Vela isn't just another cluster, it's a gravitational titan potentially rivaling the Great Attractor itself, with enough mass to yank entire galaxy clusters off course. The revelation came as a shock even to seasoned cosmologists. While mapping the cosmic web near the zone of avoidance, researchers noticed galaxies moving in ways that didn't align with the Great Attractor's pull alone. Their trajectories hinted at another massive player nearby, a gravitational shadow. By stitching together data from optical, infrared, and radio surveys, they pieced together Vela's sprawling outline, a dense knot of galaxy clusters threaded along dark matter filaments, its gravity warping local space-time like a second anchor in the cosmic stream. But here's where the debate ignites. Some scientists argue Vela isn't a separate entity at all. It could be the Great Attractor's cosmic twin, part of an interconnected attractor network where multiple superclusters act as gravitational waypoints along the same celestial highway. Think of them as two massive cities linked by an underground transit system, their combined pull shaping galactic motion across millions of light years. Others contend Vela operates independently, its influence competing with the Great Attractor in a delicate balance of forces. The clincher, Vela's position roughly 800 million light-years away, places it at a critical junction where several cosmic filaments converge, much like its more famous counterpart. What makes Vela particularly fascinating is its cloak and dagger existence. Unlike the Great Attractor, which revealed itself through galaxy motions decades ago, Vela stayed hidden until advanced redshift surveys exposed its sprawling structure. Its galaxies are so obscured by dust that their light reaches us dimmed by up to 99%, like trying to spot a lighthouse through a sandstorm. Yet despite this cosmic camouflage, Vela's gravitational fingerprint is unmistakable. Nearby galaxies veer toward it with peculiar velocities that betray its heft. The implications are profound. If Vela and the Great Attractor are linked, they might form a supercluster complex of unprecedented scale, a gravitational nexus where multiple cosmic watersheds merge. Simulations suggest such structures could channel galaxies along superhighways of dark matter, funneling them towards shared destinations over billions of years. Alternatively, if they're independent rivals, their competing tugs could explain why some galaxies like our Milky Way exhibit motions that don't perfectly align with either's predicted pull. One thing's certain, Vela's discovery proves we've barely scratched the surface of the hidden cosmos. For every structure like the Great Attractor that we've painstakingly mapped, there could be a dozen more lurking in the shadows, their gravity silently steering the universe's grand choreography. And as astronomers refine their tools to peer deeper into the zone of avoidance, who knows what other titans we'll find, each rewriting the rules of our galactic journey. The universe keeps receipts. Etched into the faint glow of the cosmic microwave background is a cryptic clue about our galaxy's high-speed journey toward the Great Attractor. This ancient radiation, the afterglow of the Big Bang, should appear perfectly uniform in every direction, a time capsule of the infant universe's smooth, fiery plasma. But when astronomers first mapped it in detail, they spotted something bizarre. A subtle temperature difference between two halves of the sky, as if someone had tilted the entire cosmos. One hemisphere glows slightly warmer, the other fractionally cooler, a discrepancy of just 1 part in 1,000, but enough to expose a staggering truth. Our galaxy isn't just drifting, it's sprinting through space at 600 kilometers per second, dragged by the Great Attractor's gravitational grip. This temperature split, called the CMB dipole, acts like a cosmic speedometer. Here's how it works. As the Milky Way barrels toward the Great Attractor, we're plowing into the microwave background radiation in that direction, compressing its wavelengths like an ambulance siren sounding higher-pitched as it races toward you. This headwind makes the attractor's side of the sky appear warmer. Conversely, the radiation behind us gets stretched as we flee from it, cooling that hemisphere's signal. The result, a lopsided universe, one that betrayed our motion long before we understood its cause. But the real revelation came when scientists subtracted this dipole from the data. What remained was the CMB's near-perfect uniformity, proof that the temperature difference wasn't some flaw in the universe's design, but a fingerprint of our own motion. It's like realizing the static on an old TV isn't random noise, but interference from a passing truck. That 600 kilometer per second peculiar velocity, astronomers speak for motion beyond cosmic expansion, pointed straight toward the constellation Centaurus, the Great Attractor's rough location. Yet the CMB dipole isn't just a directional arrow. Its intensity reveals something even more profound, the sheer scale of the forces at play. For our galaxy to move this fast, the Great Attractor must wield the gravitational pull of tens of thousands of Milky Ways, an unthinkable concentration of mass. And when researchers used this velocity to estimate the attractor's distance, the numbers aligned eerily with later observations of galaxy flows. The universe, it seems, had been broadcasting the Great Attractor's existence for 14 billion years. We just needed to learn how to listen. The irony, this discovery emerged from what scientists initially considered background noise. Early CMB mappers like the Decode satellite in the 1990s weren't hunting for the Great Attractor. They were studying the Big Bang's echo. The dipole was almost discarded as a local anomaly before its true significance clicked. Now, it's a cornerstone of cosmology, reminding us that sometimes the universe hides its biggest secrets in the subtlest shifts, a whisper of heat difference that rewrote our place in the cosmos. But here's the twist: the CMB dipole doesn't just trace the Great Attractor's pull. It captures the net effect of all gravitational tugs on our galaxy, including contributions from distant giants like the Shapley Supercluster and repulsive voids like the dipole repeller. Think of it as a cosmic balance sheet, tallying every debit and credit in gravity's ledger. And when astronomers adjust their models to account for these competing forces, something doesn't quite add up. The dipole's amplitude suggests our motion should be even faster, hinting that undiscovered structures, perhaps deeper in the zone of avoidance, are still out there, tweaking our trajectory in ways we've yet to map. What makes this humble temperature difference so revolutionary is its universality. While galaxy surveys require piecing together millions of individual observations, the CMB dipole delivers a single, clean measurement of our motion, a snapshot of gravity's influence frozen in microwaves. It's the universe's way of handing us a speeding ticket, complete with directions to the courtroom. And as next-generation telescopes like the Simons Observatory refine these measurements, we may yet decode finer details like whether dark energy's push is altering our course or if deeper attractors lurk beyond the horizon. For now, the CMB remains our most impartial witness, its subtle asymmetry a permanent record of the Great Attractor's relentless pull. Among the most compelling evidence for dark matter, the invisible scaffolding shaping the Great Attractor's pull comes from a cosmic car crash 2.4 billion light-years away. The Bullet Cluster, a pair of galaxy clusters that collided at a staggering 100 million miles per hour, didn't just confirm dark matter exists, it revealed something eerie about how this mysterious substance behaves. When these clusters smashed together, their visible matter hot gas glowing in X-rays slammed into each other like two clouds of smoke, slowing down and piling up at the collision center. But their dark matter, it barely noticed. Gravitational lensing maps showed the majority of the cluster's mass. The dark matter had sailed right through the wreckage, leaving the visible matter behind like debris in its wake. This cosmic fender bender offers a crucial clue about the Great Attractor's hidden architecture. Just as the Bullet Cluster's gravity came mostly from unseen dark matter, the attractor's immense pull suggests a similar imbalance. Think of it like a haunted house where the creaks and slamming doors reveal an unseen presence, except here, the ghosts are vast halos of dark matter warping the paths of galaxies around them. Gravitational lensing, the same technique used to map the Bullet Cluster's dark matter, hints that the attractor's core might be a dense knot of this invisible material, its gravity bending light from background galaxies into faint, stretched arcs. These distortions are like fingerprints, revealing where mass lurks even when our telescopes see nothing. Yet the Bullet Cluster's legacy goes further. Its dark matter didn't just pass through the collision untouched, it did so without interacting at all, not even with itself. This absence of friction is why dark matter can form such vast, smooth filaments around structures like the attractor, while visible matter clumps into stars and gas. It's also why the attractor's influence stretches so far. Without any drag, its dark matter's gravity reaches across millions of light years, tugging galaxies along like leaves caught in a stream. The irony, dark matter's elusiveness, the very trait that makes it so hard to detect, is what allows it to sculpt the universe's largest structures. While stars and gas get bogged down in collisions or stalled by magnetic fields, dark matter moves unimpeded, knitting together superclusters and shaping cosmic watersheds like the attractor's domain. And just as the bullet cluster gave us a snapshot of dark matter's behavior, future lensing surveys might finally unmask the attractor's shadowy skeleton, revealing whether it's a single dense nexus or a web of dark matter threads converging in space. What's thrilling is how much we've learned from absence. The bullet cluster's dark matter left no light, no heat, no radiation, just a gravitational echo. And if that echo resonates in the Great Attractor's pull, it means we're not just being dragged toward a cluster of galaxies, but toward something far stranger, a monstrous knot in the dark matter web where the universe's hidden architecture gathers its greatest strength. While the Great Attractor commands attention with its gravitational might, it's just one player in a cosmic arena where structures dwarf even our grandest terrestrial metaphors. Take the CFA2 Great Wall, a filament of galaxies stretching an astonishing 750 million light-years across the universe. To grasp that scale, picture a strand so vast it could connect the Milky Way to the Andromeda Galaxy 150,000 times over. This isn't just a cluster or supercluster, it's a galactic freeway. It's galaxies strung along dark matter threads like pearls on an endless necklace. Yet compared to the Great Attractor, which spans a mere 300 million light-years, the Great Wall redefines what we consider colossal in the cosmos. What makes these megastructures so perplexing isn't just their size, it's how they challenge a foundational principle of cosmology. The idea that on large enough scales, the universe should appear roughly uniform like a well-mixed batter. Known as the cosmological principle, this assumption underpins everything from Einstein's equations to our models of cosmic expansion. Yet walls like CFA2 and attractors like our own seem to flout this rule, clustering matter in ways that defy expectations. Imagine pouring sand into a jar, only to find it spontaneously arranging into towering ridges instead of spreading evenly. That's the level of anomaly we're confronting. The irony, these structures might not actually break the rules. Simulations suggest that while galaxies appear densely packed in walls and attractors, their spacing could still fit within statistical homogeneity when averaged across even larger volumes. It's like zooming out from a forest up close. Trees cluster in groves, but from space the canopy looks continuous. Yet some astronomers argue that CFA2's scale pushes the limits, with its galaxies aligned too coherently for comfort. If future surveys uncover even larger walls, some theorists speculate about structures over 1 billion light-years long. The principle might need revisiting entirely. Here's the twist: the Great Attractor and the CFA2 Great Wall might be two sides of the same cosmic coin. Both represent nodes where dark matter's web knots tighter, funneling galaxies into dense gatherings. While the attractor pulls us inward, the Great Wall exemplifies how matter organizes into vast sheets, outlining the universe's hidden skeleton. And just as the attractor has rivals like Shapley, the Great Wall isn't alone. It shares the stage with titans like the Sloan Great Wall and the Hercules Corona Borealis counterpart, each stretching the definition of structure itself. What's truly humbling is how these discoveries reshape our cosmic address. We once imagined galaxies floating like islands in a dark sea. Now we know they're threads in a tapestry of walls, attractors, and voids, a cosmic metropolis where even the empty spaces play gravitational chess. And as telescopes probe deeper, one question lingers. If the Great Wall and attractor seem improbably vast today, what awaits beyond the horizon of our current maps? While the Great Attractor pulls us toward unfathomable density, our cosmic backyard tells a different story, one of staggering emptiness. Nestled inside a vast bubble spanning 2 billion light-years, the Milky Way resides in one of the universe's loneliest neighborhoods, the KBC Void. Named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, this region is so sparsely populated that if the cosmos were a bustling city, we'd be living in its most desolate suburb. Galaxies here are scattered like distant campfires in an endless desert, their numbers far fewer than the universe's average. This void isn't just empty, it's a gravitational desert. Its lack of mass warping our perception of the cosmic tides carrying us toward the attractor's crowded shores. The KBC Void's existence flips a cosmic assumption on its head. For decades, astronomers presumed our corner of space was roughly average, neither exceptionally dense nor unusually sparse. But when researchers tallied galaxy counts across our local universe, the numbers painted a startling picture. While typical regions host about 5,000 galaxies per cubic billion light-years, our void contains barely half that amount. That deficit creates a gravitational vacuum, amplifying the contrast between our quiet pocket and the attractor's teeming metropolis. Imagine floating in a life raft near a whirlpool. The calmer your surroundings, the more dramatic the current's pull feels. That's precisely how the KBC Void magnifies the Great Attractor's influence, by making our motion through space seem even more extreme against the void's stillness. But emptiness isn't just a backdrop, it's an active player. The KBC Void's sparse mass means it exerts less gravitational pull than denser regions, effectively functioning like a gentle push. When combined with the dipole repeller's repulsive effect, it helps explain why our galaxy's path doesn't point precisely at the attractor. These competing forces, the attractor's tug, the repeller's push, and the void's neutrality, create a three-way gravitational dance, each shaping our trajectory in ways we're only beginning to untangle. It's a reminder that cosmic motion isn't dictated by a single force, but by the delicate balance of presence and absence across scales almost too vast to comprehend. What's truly humbling is how this void reframes our place in the cosmos. Far from being at the center of anything, we're drifting through a cosmic underdog, a region where galaxies are so rare that spotting one feels like finding an oasis. And just beyond this emptiness, the Great Attractor looms, its gravity bending the paths of galaxies like ours as we stream toward the universe's hidden hubs of power. The KBC Void isn't just empty space, it's the blank canvas against which the attractor's might is thrown into sharp relief, proving that sometimes nothingness speaks as loudly as mass. Right now, the Milky Way is racing toward the Great Attractor at 14 million miles per hour, but will we ever actually reach it? The answer hinges on a cosmic race against time, where the universe's expansion and gravity's pull are locked in a tug-of-war for our galactic fate. Current projections suggest that in roughly 5 billion years, our galaxy could merge with the Andromeda Galaxy, sparking a celestial dance that might redirect our trajectory entirely. Picture two spiral galaxies, each with hundreds of billions of stars, colliding in slow motion, their gravity weaving them into a single, glowing ellipse. This isn't science fiction, it's an inevitability written in the motions of nearby galaxies. But here's where the Great Attractor complicates things. Even as we spiral toward Andromeda, the attractor's gravity continues pulling both galaxies toward its hidden core. The result, a potential three-way pileup of cosmic proportions. Simulations of this distant future reveal something startling. While the Milky Way and Andromeda will eventually merge, their combined mass still won't be enough to escape the Great Attractor's grasp. Instead, the newly formed Andromeda Galaxy, along with the rest of our local group, could become part of a vast river of galaxies flowing toward the attractor's gravitational well. Imagine a whirlpool slowly gathering floating leaves. Our galactic neighborhood is destined to join that cosmic current, but timing is everything. The universe's expansion is accelerating thanks to dark energy's mysterious push. Over billions of years, this expansion could stretch the distance between galaxy clusters so dramatically that even the attractor's pull might not be enough to overcome it. We're in a race where the finish line keeps moving, yet the most intriguing wild card isn't dark energy, it's the attractor's own motion. Recent studies suggest the Great Attractor isn't stationary. It's being pulled toward the even more massive Shapley Supercluster, like a planet orbiting a star. If true, our collision course isn't a straight line, but a spiraling path through an ever-shifting gravitational landscape. Future galaxies might look up to see the attractor not as a fixed point in the sky, but as a moving target, its position warped by deeper cosmic currents. What does this mean for life billions of years from now? If any civilizations exist in that distant era, their night sky would be unrecognizable. The Milky Way and Andromeda's merger will scatter stars into dazzling new patterns, while the Great Attractor's pull could stretch their galaxy's shape like taffy. But here's the twist. By then, the attractor itself might have merged with other superclusters, becoming part of an even larger structure we can't yet imagine. The universe's largest collisions aren't just events, they're chapters in an epic saga where gravity writes the plot, and galaxies are merely actors on a stage billions of light years wide. One thing's certain, whether we merge with the attractor or drift forever just out of reach, our galaxy's journey is far from over. We're not just passengers on this ride, we're witnesses to a cosmic realignment that will unfold long after our sun has faded. And that's the most humbling revelation of all. The Great Attractor isn't just pulling stars, it's pulling time itself. Long before galaxies formed, the infant universe was a roiling sea of hot plasma, ringing with sound waves that left an indelible imprint on the cosmos. These primordial vibrations, called baryon acoustic oscillations, froze into the fabric of space-time as the universe expanded, leaving behind a cosmic fingerprint we can still detect today. Picture dropping a pebble into a pond, watching ripples spread outward, then instantly freezing the water solid. That's essentially what happened 14 billion years ago, except the pebble was a quantum fluctuation, and the pond was the entire observable universe. These frozen ripples became the scaffolding for everything we see, galaxies, clusters, and even the Great Attractor itself. The brilliance of baryon acoustic oscillations lies in their predictability. Those early sound waves traveled at a known speed before the universe cooled enough to freeze them in place, creating a characteristic scale about 500 million light-years that repeats like a cosmic yardstick. When astronomers map galaxies today, they find this signature distance echoing through space. Galaxies are slightly more likely to be separated by this exact span than any other. It's as if the universe stamped a grid into existence, and every structure from isolated dwarf galaxies to the attractor's sprawling web aligns with its ghostly blueprint. Here's where it gets revelatory. When scientists overlay BAO maps with the Great Attractor's position, the overlap is uncanny. The attractor sits at a nexus where these ancient oscillations piled matter into dense knots, like a resonance amplifying sound at certain frequencies. Imagine blowing across soda bottles filled to different heights, each produces a distinct note. The universe did something similar, with the Great Attractor forming where multiple notes of these frozen waves harmonized, concentrating mass into a gravitational hotspot. But BAO does more than explain the attractor's location. It helps measure its pull. By comparing the expected distribution of galaxies based on oscillations to their actual motions revealed by redshift surveys, astronomers can calculate how much the attractor's gravity is warping local space. The discrepancies are striking. Galaxies near the attractor aren't just slightly off-grid, they're streaming toward it like iron filings pulled by a magnet, their paths twisted by dark matter's invisible hand. What makes these oscillations so valuable is their independence from other cosmic measuring sticks. While methods like supernova distances or CMB analysis rely on specific phenomena, BAO works like a universal ruler, equally valid across all epochs of the universe. It's why projects like the Sloan Digital Sky Survey and DAISY, the Dark Energy Spectroscopic Instrument, devote thousands of nights to mapping millions of galaxies. Each data point sharpens our view of these frozen waves, and by extension, the hidden structures they outline. Yet mysteries remain. Some regions, including parts of the attractor's domain, show BAO patterns that are fainter than expected, as if something is damping the oscillation's echoes. Could unknown physics be at play, or are we seeing the limits of our maps where dust or peculiar velocities muddy the signal? The answers might lie in next-generation surveys, which will probe BAO at finer resolutions, potentially revealing substructures within the attractor that current telescopes can't resolve. One thing's certain, baryon acoustic oscillations are more than relics, they're active participants in shaping the cosmos. The Great Attractor doesn't just occupy space, it embodies a rhythm set in motion when the universe was a seething plasma. Its gravity conducting galaxies into alignment with a beat 14 billion years in the making. And as we decode more of these frozen waves, we're not just studying the attractor, we're listening to the universe's first symphony. The Great Attractor may dominate our galactic neighborhood, but it's far from the universe's only heavyweight. In 2003, astronomers analyzing data from the Sloan Digital Sky Survey stumbled upon something that redefines colossal, a galactic filament so vast it could swallow the attractor whole. Stretching 1.4 billion light-years across, the Sloan Great Wall isn't just a structure, it's a cosmic continent, a sprawling metropolis of galaxies strung along dark matter threads like lights on an infinite freeway. To grasp its scale, imagine a chain so long it could loop from the Milky Way to Andromeda 300,000 times and still have room to spare. This discovery sent shockwaves through cosmology, not just for its sheer size, but for what it implies about the Great Attractor's place in the pecking order. Where the attractor is a gravitational hub pulling galaxies into its orbit, the Sloan Great Wall is an entire ecosystem of such hubs, woven into a single, interconnected web. Think of it like comparing a bustling city to an entire nation. The attractor might be a powerful metropolis, but the wall is the country it resides in, with countless other cities dotting its expanse. The implications are staggering. If the attractor's pull feels irresistible to us, what unseen forces might the wall exert on it? Yet here's where the controversy ignites. The Sloan Great Wall's existence seems to flout a fundamental rule called the cosmological principle, which states that, on large enough scales, the universe should look roughly the same everywhere. A structure this massive, spanning nearly 5% of the observable universe, throws that assumption into doubt. Some theorists argue it's not a true anomaly, just a statistical fluke where smaller filaments happen to align in our surveys. Others counter that the wall's coherence, its galaxies clustering too neatly along a single plane, suggests something deeper, perhaps even a flaw in our understanding of how dark matter sculpts the cosmos. The Great Attractor adds another layer to this puzzle. While it's dwarfed by the Sloan Great Wall, its gravitational influence might not be. Imagine two magnets, one enormous but diffuse, the other smaller but intensely concentrated. The wall's mass is spread across such an incomprehensible volume that its local gravity could be weaker than the attractor's, meaning our galaxy might still feel the attractor's tug more acutely, even as both structures dance to the tune of larger cosmic forces. What's truly humbling is how these discoveries reframe our cosmic address. We're not just falling toward the Great Attractor, we're part of a vast hierarchical web where structures nest inside larger structures, each governed by the same invisible rules. The attractor might be our immediate destination, but the Sloan Great Wall reminds us that the universe's true architecture operates on scales so vast, they bend the limits of human comprehension. And as surveys map deeper into space, one question lingers. If this is what we've found so far, what other titans are waiting in the dark? Measuring the universe's expansion should be straightforward. Point a telescope, crunch the numbers, and voila. Yet astronomers are locked in a heated debate over conflicting results that threaten to upend our cosmic playbook. It's called the Hubble tension. Two gold standard methods for calculating the expansion rate, H0, disagree by nearly 10%. A discrepancy that sounds small until you realize it spans 14 billion years of cosmic history. One camp, using the cosmic microwave background's pristine snapshot of the infant universe, gets an expansion rate of 67 kilometers per second per megaparsec. The other, relying on supernova in our cosmic backyard, insists it's 73. At first glance, it seems like someone's math is wrong. But what if the culprit isn't a calculation error, but the Great Attractor's hidden hand warping our local measurements? Here's why this matters. The supernova method hinges on a simple premise. By tracking how fast nearby galaxies are receding, we can extrapolate the universe's expansion. But this assumes those galaxies are moving only due to cosmic expansion, not gravitational tugs from nearby structures. Enter the Great Attractor, whose immense gravity distorts galactic motions across our entire neighborhood. Picture trying to measure a river's current while swimming in a whirlpool. Your readings would be skewed by the swirling water around you. Similarly, if the attractor is yanking the Milky Way and nearby galaxies toward it at 14 million miles per hour, that motion contaminates our local H0 measurements, making expansion appear faster than it truly is. The plot thickens when we zoom out. The CMB method, which measures expansion from the universe's earliest light, isn't affected by local flows. It sees the pure expansion signal unimpeded by nearby gravity wells. This could explain why the two methods diverge. One captures the universe's true expansion, while the other mixes that signal with our galaxy's peculiar velocity toward the attractor. Some researchers estimate this gravitational interference could account for up to half the observed discrepancy, a revelation that turns the Hubble tension from a crisis into a clue, pointing straight toward the attractor's far-reaching influence. Yet not all astronomers are convinced. Skeptics argue that even the attractor's immense gravity can't fully explain the H0 gap. The required peculiar velocities would be far larger than observed. Others propose wilder solutions. Maybe dark energy's strength varies across space, or perhaps our universe isn't as uniform as we thought, the most radical suggestion. That we're caught in a Hubble bubble, a region of space where local density variations, including the attractor's pull, create a distorted view of expansion, like a funhouse mirror reflecting a warped cosmic portrait. What makes this debate so pivotal is its stakes. If the attractor is biasing our measurements, it means we've been misreading one of cosmology's most fundamental constants, a number that dictates the universe's age, size, and ultimate fate. Correcting for this skew could reconcile the Hubble tension overnight, preserving our standard model of cosmology. But if the discrepancy persists even after accounting for large-scale flows, we might need to rewrite physics itself, perhaps introducing new particles, dimensions, or forces. The Great Attractor, it seems, isn't just pulling galaxies, it's pulling the rug out from under our understanding of cosmic expansion. As next-generation telescopes like JWST and the Vera Rubin Observatory refine these measurements, one thing becomes clear. The universe's expansion rate isn't just a number. It's a story, one where local anomalies like the attractor might hold the key to global truths, and where the biggest mysteries often hide in the gaps between what we measure and what we expect. Whether this cosmic detective story ends with revised models or revolutionized physics, the Great Attractor remains a prime suspect, its gravity subtly warping not just space, but our very perception of reality. Even as the Great Attractor's gravity pulls galaxies into its web, an invisible force works against it, stretching the very fabric of space itself. Dark energy, the mysterious repulsive force accelerating the universe's expansion, isn't just pushing galaxies apart, it's actively undermining the attractor's growth. Picture a cosmic tug-of-war where one team keeps moving the rope further apart. Gravity gathers matter into clusters, while dark energy stretches the space between them, making it harder for new structures to form. The result, a universe where the attractor's dominion may already have peaked, its influence slowly diluted by the relentless expansion of space. To grasp this balancing act, think of the universe as a balloon inflating faster and faster. Draw dots on its surface to represent galaxies. As the balloon expands, the dots move apart. Now imagine some dots are clustered close together, symbolizing the Great Attractor's gravitational pull. At first, gravity holds these dots in place against the balloon's stretch, but as inflation accelerates, the space between even tightly bound dots widens, making it harder for new dots to join the cluster. That's precisely what's happening on a cosmic scale. Dark energy isn't just expanding the universe, it's raising the gravitational cost of building structures like the attractor, forcing matter to fight against an increasingly powerful outward push. This counterbalance plays out in startling ways. Computer simulations show that while dark energy makes up nearly 70% of the universe's energy budget, its effects only became dominant around 5 billion years ago, a cosmic blink when compared to the attractor's 13 billion-year formation. Before that epoch, gravity reigned supreme, allowing titans like the attractor to assemble. Now, dark energy's acceleration means any structures not already bound by gravity may never fully coalesce. The attractor isn't shrinking, it's just becoming more isolated, like an island slowly drifting further from shore. Yet dark energy's influence isn't uniform. Within galaxy clusters, gravity still dominates locally, which is why the attractor's core remains tightly bound. But on larger scales, like the filaments connecting it to other superclusters, dark energy's stretch is winning. Recent observations reveal these cosmic highways are thinning over time, their delicate strands of dark matter straining against expansion. It's as if the universe's scaffolding is being pulled taut, with the attractor clinging to its section even as the overall web grows more diffuse. What makes this duel so fascinating is its time sensitivity. Had dark energy's acceleration kicked in earlier, the attractor might never have reached its current size. Later, and it could have grown even more massive. Instead, we're witnessing a Goldilocks moment, a window where both forces are visible in the cosmic record. Future telescopes like the Nancy Grace Roman Space Telescope will map this transition in detail, revealing whether dark energy's grip is strengthening or if unknown physics might yet tip the scales back toward gravity. One thing's certain, the attractor's fate is written in this push and pull. While it won't vanish entirely, its era of growth may be over, not because it's losing mass, but because the universe is literally expanding around it. Like a castle on a receding tide, the attractor stands as a relic of a bygone cosmic age, its gravitational might now competing with the vacuum's silent, unstoppable stretch. And in that tension lies a profound truth: the universe isn't just shaped by what's present, but by the delicate balance between what pulls and what pushes. For centuries, astronomers could only guess at the Milky Way's exact motion through the cosmos until a European Space Agency mission named Gaia transformed educated estimates into pinpoint precision. Launched in 2013, this unassuming spacecraft didn't just map stars. It orchestrated a revolution in cosmic cartography, measuring the positions and movements of over 1 billion stars with staggering accuracy. Think of it as upgrading from a hand-drawn sketch to a high-resolution 3D movie of our galaxy's dance through space. And when Gaia team crunched the numbers, they delivered a revelation. Our velocity toward the Great Attractor wasn't just a rough approximation anymore. It was a hard, gleaming fact: 630 kilometers per second, with an error margin smaller than the speed of a commercial jet. The magic lay in Gaia parallax method. By observing each star from slightly different angles as Earth orbited the Sun, the spacecraft calculated stellar distances with unprecedented precision, like judging an object's distance by holding a finger up and alternating which eye you close. But Gaia didn't stop there. It tracked stars' subtle shifts over time, capturing their motions in 3 dimensions. This allowed astronomers to disentangle our galaxy's movement from the star's own orbits within it, isolating the Milky Way's true trajectory through intergalactic space. The result, a 3D vector pointing unmistakably toward the Great Attractor, cutting through the noise like an arrow. Visualizing this path is where the data truly comes alive. Picture our galaxy not as a static spiral, but as a ship plowing through a cosmic sea, its stars streaming behind it like wake from a prow. Gaia animations reveal something startling. We're not just drifting toward the attractor, we're spiraling slightly, as if caught in a gravitational eddy. This subtle twist hints at unseen dark matter substructures tugging at us along the way, their fingerprints etched into the curvature of our path. Yet Gaia revelations didn't stop at velocity. By mapping thousands of nearby galaxies' motions alongside the Milky Way's, it exposed a broader truth. We're not alone in this journey. Entire galaxy clusters are flowing with us like leaves swept downstream in a shared current. Some move faster, some slower, but all converge toward the same invisible basin. This quiet avalanche of galaxies, as one researcher called it, suggests the attractor's influence isn't uniform. It's sculpting a gradient of motion across millions of light years, with our galaxy somewhere in the middle of the pack. The most humbling insight, Gaia confirmed that even at 14 million miles per hour, we'll never actually reach the Great Attractor. The universe's expansion is stretching space between us faster than gravity can pull us together. Instead, we're destined to orbit its outskirts eternally, like a moth circling a flame just beyond its grasp. This cosmic irony, that the force dictating our motion will forever remain out of reach, is a testament to how much Gaia has refined our cosmic self-awareness. No longer are we guessing at the universe's tug. We're measuring it star by star with the precision of a master clockmaker, and every new data release peels back another layer of the attractor's secrets, proving that sometimes the key to understanding the distant cosmos lies in mapping our own backyard with obsessive detail. Mapping the Great Attractor's gravitational web requires more than just peering at the sky. It demands a cosmic census on an unprecedented scale. Enter the Baryon Oscillation Spectroscopic Survey, or BOSS, a groundbreaking project that transformed our view of large-scale structure by meticulously measuring over 1.5 million galaxies. Imagine assembling a jigsaw puzzle where each piece is a galaxy, and the final image reveals the universe's hidden skeleton. That's precisely what BOSS achieved. Using the Sloan Foundation telescope in New Mexico, this survey didn't just catalog galaxies. It traced the delicate fingerprint of baryon acoustic oscillations across billions of light years, exposing the attractor's role in the cosmic web with breathtaking clarity. What sets BOSS apart is its 3-dimensional precision. While most sky surveys plot galaxies as flat points on a map, BOSS added depth by measuring each galaxy's redshift, the stretching of light waves caused by cosmic expansion. This allowed researchers to construct a volumetric atlas of the universe, where galaxies cluster along dark matter filaments like dew on a spider's web. Within this labyrinth, the Great Attractor emerges as a dense knot where multiple filaments converge, its gravity warping the surrounding cosmic web like a boulder resting on a stretched sheet. The sheer scale of BOSS maps is staggering. They cover a volume equivalent to a cube 20 billion light-years on each side, with the attractor sitting at a pivotal crossroads in this vast network. The real breakthrough came when BOSS team compared their maps to theoretical models. The observed distribution of galaxies matched predictions for how baryon acoustic oscillations should sculpt the universe, except near the attractor. Here, galaxies veered off course, their positions skewed by its immense gravity. It's like watching water flow downstream, only to notice a whirlpool diverting the current. By quantifying these deviations, BOSS revealed that the attractor's influence extends far beyond its visible mass. tugging on galaxies across a region spanning 300 million light-years. This gravitational reach suggests the attractor isn't just a cluster, it's a nexus where multiple cosmic watersheds merge, funneling matter along filaments like rivers feeding an inland sea. But BOSS legacy goes deeper. Its data exposed a curious asymmetry in the cosmic web around the attractor. On one side, filaments appear more densely packed, as if compressed by some ancient pressure wave. On the other, they're stretched thinner, like taffy pulled to its limit. Some theorists speculate this imbalance could trace back to primordial sound waves in the early universe, ripples that froze into place as matter congealed, leaving the attractor anchored to a peak in this fossilized undulation. Others propose it's evidence of even larger structures beyond our current maps, their gravity warping the attractor's domain from afar. What's unmistakable is how BOSS transformed abstract theory into observable reality. Before its findings, the Great Attractor's place in the cosmic web was largely inferred. Now we can see it, a gravitational lodestone embedded in a web of dark matter and galaxies, its pull written into the very fabric of space. And as future surveys build on BOSS foundation, each new data point sharpens our view of this hidden architecture, proving that sometimes to understand the universe's grandest mysteries, you must first map its shadows. Among the cosmic microwave background's subtle fluctuations, those faint whispers of the Big Bang's afterglow, lies a chilling anomaly that has puzzled astronomers for decades. Known simply as the cold spot, this patch of sky, spanning nearly 1.8 billion light-years, glows slightly cooler than its surroundings, a discrepancy of just a few millionths of a degree, but one that defies easy explanation. What makes it even stranger, this frigid void aligns eerily with the Great Attractor's direction, as if the universe is pointing a cosmic arrow toward hidden forces shaping our galactic journey. Some researchers argue it's a supervoid, a vast, underdense region of space where the lack of matter subtly dims the CMB. Others propose something far more radical, that this cold spot could be a bruise from a collision with another universe, a scar etched into the fabric of reality itself. The supervoid theory seems intuitive at first glance. If the cold spot is an enormous void, a cosmic desert where galaxies are sparse, its emptiness could slightly redshift the CMB photons passing through it, much like light dimming as it travels through fog. Surveys have indeed identified a sparse region called the Eridanus supervoid overlapping the cold spot's location, but here's the catch. Its size and depth don't fully account for the temperature drop. Calculations suggest this void's gravitational influence would only cool the CMB by about 20% of what's observed. It's like finding a puddle at the bottom of a hill, but realizing the slope isn't steep enough to have created such a splash. That discrepancy fuels wilder hypotheses. Could the cold spot be evidence of a cosmic texture, a defect in space-time left over from the universe's violent birth? Theoretical models suggest such imperfections could create localized temperature dips, but they'd likely be far smaller than the observed cold spot. Then there's the multiverse angle. In some speculative theories, our universe might have collided with a bubble of another reality during cosmic inflation, leaving behind a gravitational imprint that cooled this patch of sky. Imagine two soap bubbles gently brushing in a sink. The spot where they touch would warp slightly, preserving a memory of the encounter. Yet the Great Attractor's alignment with the cold spot adds another layer of intrigue. If the attractor's gravity is pulling us and countless other galaxies toward this enigmatic region, could the cold spot's underlying cause be amplifying that motion? Some simulations suggest that an ultramassive structure beyond the attractor, hidden by the zone of avoidance, might be warping both the CMB and galactic flows in tandem. Picture a ship sailing toward an iceberg. The crew might notice the ice first, but the real danger lies beneath the surface, unseen. Similarly, the cold spot could be the visible tip of a deeper gravitational anomaly, one that's yanking the attractor, and us along with it, toward something even more colossal. Skeptics counter that the alignment could be coincidence. The universe is vast and random correlations inevitably appear in large datasets. But the odds of such a pronounced cold region lining up with the attractor's pull, a direction already fraught with gravitational mysteries, give pause. Future CMB experiments like the Simons Observatory aim to study the cold spot in finer detail, searching for telltale patterns in its polarization that could distinguish between a supervoid, a texture, or something entirely unforeseen. What's undeniable is how the cold spot magnifies the Great Attractor's mystique. Whether it's a void, a relic of inflation, or a window into other realities, its presence whispers that our understanding of cosmic structure is incomplete. The universe doesn't just hide its secrets in darkness, it encodes them in the faintest of temperature dips, waiting for us to decipher their meaning. The Great Attractor isn't just a gravitational titan, it's a cosmic predator, a relentless devourer of galaxies that has spent billions of years feasting on smaller clusters unlucky enough to wander into its grasp. Picture the Norma cluster, a dense swarm of hundreds of galaxies being slowly pulled apart by the attractor's insatiable hunger, its stars stripped away like flesh from bone. Time-lapse simulations reveal this gruesome process in eerie detail. Galaxies spiral toward the attractor's core, their orbits tightening like nooses until they collide, merge, or are torn into streams of stars, a phenomenon astronomers call galactic cannibalism. These mergers aren't quick, violent events. They're slow, methodical feasts playing out over cosmic timescales where gravity acts as the ultimate digestive system, breaking down entire galaxies into raw material for the attractor's growing bulk. What makes this predation so terrifying is its inevitability. Galaxies entering the attractor's gravitational jaws don't stand a chance. Their fate is sealed the moment they cross a threshold called the virial radius, where the attractor's gravity overcomes their own. From there, they're shredded by tidal forces stretched into long, luminous ribbons known as tidal streams. Some simulations show galaxies like NGC 4839, once proud spirals, reduced to ghostly trails of stars orbiting the attractor's core like cosmic crumbs. These streams aren't just debris, they're fossil records of past meals, visible evidence of the attractor's relentless consumption. Yet the attractor doesn't dine alone. It's part of a hierarchy of predators where smaller clusters like Norma are themselves cannibalizing dwarf galaxies even as they're consumed. It's a galactic food chain with the attractor at the top, its gravity orchestrating a slow-motion feast that reshapes entire regions of space. The eerie beauty of this process lies in its order. Mergers aren't random chaos but carefully choreographed dances dictated by dark matter halos. As galaxies spiral inward, their dark matter envelopes merge first, creating a gravitational scaffold that guides the visible matter into place, like an invisible hand arranging silverware before a meal. The attractor's hunger also leaves behind gruesome remnants. At its core lies a supermassive black hole, gorging on the gas and stars ripped from its victims. This black hole isn't just a passive participant, it's an active predator in its own right, flaring brightly as it consumes, its outbursts heating surrounding gas to millions of degrees. These active galactic nuclei act like cosmic belches, signaling another galaxy's demise. Meanwhile, the attractor's outer regions are littered with orphaned stars, those flung free during mergers, now wandering the darkness between galaxies like lost souls. But here's the twist, the attractor isn't unique. This predatory behavior is universal. From the Virgo cluster to the Coma Supercluster, galaxies are constantly merging, their fates dictated by gravity's unforgiving math. What sets the attractor apart is its scale and our place in its menu. The Milky Way, too, is caught in this cosmic current, destined to one day join the feast not as a diner but as prey. Current projections suggest that in about 4.5 billion years, our galaxy's merger with Andromeda will form a new elliptical galaxy, which the attractor will eventually consume. It's a humbling reminder that in the grand scheme of things, even galaxies are temporary, glimmering morsels in the attractor's endless banquet. What's most astonishing isn't the destruction, but the rebirth. The stars torn from devoured galaxies don't vanish. They're recycled, becoming part of new generations of stars and planets. The attractor isn't just a destroyer. It's a crucible forging new cosmic structures from the remnants of the old. Its hunger isn't mindless. It's the engine of cosmic evolution, a force that's shaped the universe as we know it. And as we watch simulations of galaxies spiraling toward their doom, we're not just witnessing death, we're seeing the universe's way of reinventing itself, one merger at a time. Einstein once called the cosmological constant his greatest blunder, a fudge factor he'd inserted into his equations to keep the universe static, only to later reject when expansion was discovered. But what if his real mistake wasn't adding that term, but assuming the universe should be uniform in the first place? The Great Attractor and its colossal neighbors present an inconvenient truth. The cosmos might be far lumpier than we ever imagined. At scales exceeding 1 billion light-years, we're finding structures so vast they make the Sloan Great Wall look provincial, a cosmic variance problem that rattles the foundation of modern cosmology. The cosmological principle, that bedrock assumption that the universe looks roughly the same everywhere when viewed at large enough scales, starts to crumble under these discoveries. Imagine stirring batter until it's smooth, only to pull out a spoonful and find streaks of unmixed flour clustered together. That's essentially what surveys like BOSS and 2DF have revealed. Galaxies aren't just randomly sprinkled through space, but arrange themselves in a foam-like pattern of walls and voids stretching far beyond theoretical predictions. The Great Attractor sits at the heart of this anomaly, a gravitational node so massive it creates visible ripples in the distribution of galaxies hundreds of millions of light-years away. What makes this especially puzzling is how early these structures emerged. The cosmic microwave background shows a universe that was nearly uniform at 380,000 years old, with density variations of just 1 part in 100,000. Yet somehow, within a few billion years, matter clumped into behemoths like the Attractor and the Hercules Corona Borealis Great Wall, a structure spanning 10 billion light-years that somehow escaped notice until 2013. The math suggests there hasn't been enough time since the Big Bang for gravity alone to sculpt such titans. It's like finding a redwood forest in a field that was sown with grass seeds yesterday. Einstein's blunder takes on new irony here. His cosmological constant, later revived as dark energy, was meant to counteract gravity's clumping effect. But now we're seeing gravity win anyway, building structures so large they strain our models of how the universe evolves. Some theorists propose radical solutions, maybe dark energy weakened in certain regions, allowing matter to aggregate faster. Others suggest these megastructures are relics of primordial quantum fluctuations, random wrinkles in spacetime's fabric that got stretched to cosmic proportions during inflation. The most unsettling possibility, that we're witnessing a selection bias writ large. Just as early astronomers assumed Earth was the center of the solar system, we might be mistaking our local galactic neighborhood for the universe's true character. If the Great Attractor is an outlier, one dense knot in an otherwise uniform cosmos, its existence wouldn't violate the cosmological principle. But that raises an even stranger question. What are the odds we'd happen to live right next to the exception? It's like winning a lottery where the prize is existential vertigo. As next-generation telescopes like the Vera Rubin Observatory map deeper into space, they'll test whether the Attractor's ilk are rare anomalies or signs of a deeper truth, that the universe isn't just lumpy, but fundamentally inconsistent in ways that force us to rewrite cosmic rulebooks. Either way, Einstein's ghost might be smiling. His blunder could yet prove prescient, not for the term he inserted, but for the uniformity he assumed. In a cosmos where walls stretch billions of light-years and attractors hide behind galactic dust, perhaps smoothness was never more than a convenient illusion. Hydrogen might be the universe's simplest atom, but its faint radio whispers reveal some of the cosmos' most dramatic motions. Spread thinly between galaxies, vast clouds of neutral hydrogen gas act like tracer dye in a cosmic river. Their subtle shifts in wavelength exposing currents flowing straight toward the Great Attractor. Radio telescopes tuned to 21 centimeters, the precise wavelength cold hydrogen emits when its electron flips spin, have mapped these flows in stunning detail, uncovering streams of gas moving at speeds that defy the universe's expansion. It's as if we've sprinkled the void with luminous dust, watching it swirl toward a hidden drain. The key lies in the Doppler effect. As hydrogen clouds move toward us, their 21-centimeter radiation gets compressed, shifting toward shorter, bluer wavelengths. When they recede, the light stretches redder, but near the Great Attractor, something bizarre happens. Entire swaths of gas show both shifts simultaneously, their spectral lines smeared like a train whistle changing pitch as it races past. This double-peaked profile betrays gas caught in a cosmic tug-of-war, some particles accelerating toward the attractor's gravity well, others still resisting its pull. The resulting data looks less like a tidy line and more like a seismograph during an earthquake, its jagged peaks revealing turbulence on scales spanning millions of light years. Among the most compelling evidence comes from the Hi-4Pi survey, which mapped the entire sky's hydrogen using radio telescopes in Germany and Australia. Its data revealed vast filaments of gas, some spanning over 50 million light-years, streaming toward the attractor at peculiar velocities up to 300 kilometers per second. Picture tracing smoke drifting toward a hidden fan. The patterns expose airflow even when the source is obscured. Similarly, these hydrogen currents outline the attractor's influence far beyond where optical telescopes can see, particularly through the Milky Way's dust-choked zone of avoidance. In regions where galaxies are too dim to spot, neutral hydrogen glows faintly at 21 centimeters, its radio light slicing through the cosmic fog. What's startling is how this gas moves differently than the galaxies it surrounds. While entire galaxies respond to the attractor's pull on timescales of billions of years, hydrogen, less anchored by gravity, flows faster, like leaves outpacing logs in a river. The most extreme flows form what astronomers call high-velocity clouds, barreling toward the attractor at over 500 kilometers per second. Some appear completely detached from any visible galaxy, suggesting they're the shredded remains of dwarf galaxies torn apart during earlier close passes. Others stretch into tendrils hundreds of thousands of light-years long, marking the trajectories of past galactic encounters like contrails in a celestial sky. These observations don't just reveal motion, they expose the attractor's feeding mechanism. Hydrogen is the raw material for new stars, and the gas now funneling toward the attractor will eventually ignite into future generations of suns. Radio maps show some filaments wrapping around the attractor's core like spokes on a wheel, their gas compressed enough to begin glowing in X-rays as it heats up. It's a slow-motion feast where the main course hasn't even reached the table yet. A banquet where gravity does the cooking over cosmic timescales, yet mysteries remain. Some hydrogen clouds move too fast, their velocities exceeding what the attractor's visible mass should allow. Others flow perpendicular to expected paths, hinting at unseen dark matter substructures redirecting the currents. And in the attractor's immediate vicinity, hydrogen becomes conspicuously scarce, either consumed by star formation or ionized into invisibility by intense radiation. Each anomaly is a clue helping astronomers reconstruct the attractor's hidden anatomy one spectral line at a time. What makes this 21-centimeter window so powerful is its universality. While galaxies form only in dense knots of dark matter, neutral hydrogen permeates even the emptiest voids, tracing flows across the entire cosmic web. Future telescopes like the Square Kilometre Array will amplify this view, detecting hydrogen clouds 10 times fainter than current limits. With each new survey, we're not just mapping gas, we're watching gravity's choreography in real time, as the universe itself steers the currents toward its most secret depths. The Great Attractor's gravitational enigma has long captivated not just scientists, but storytellers. It's invisible, might woven into the fabric of science fiction as a cosmic boogeyman or galactic crossroads. Take Mass Effect, where the attractor, reimagined as a gravitational anomaly, becomes the Reaper's hiding place, a dark corner of the galaxy where ancient machines lurk. The game's lore twists real astronomy into a narrative device. Instead of pulling galaxies, this fictional attractor traps ships in a relativistic prison, playing on public fascination with gravity's unstoppable grip. Yet the reality is far stranger. No known force could compress space so violently without spacetime itself unraveling. Star Trek takes a softer approach. In the Next Generation, the attractor appears as a navigational hazard, its gravity well threatening to strand the Enterprise unless they harness a metaphasic shield, a classic Trek technobabble solution. What's revealing is how the episode downplays the attractor's scale. In reality, no starship could escape a structure that tugs entire superclusters. Hollywood often conflates black holes with large-scale gravitational anomalies, but the attractor's power comes from distributed mass, not a single crushing singularity. The trope of gravity as villain reaches its peak in Interstellar, where Gargantua's time-warping tides mirror how pop culture misrepresents cosmic pulls. While the film's black hole physics was vetted by Nobel laureate Kip Thorne, its depiction of concentrated gravity ignores the attractor's diffuse nature. No spinning disks or watery planets here, just a vast, relentless tide nudging galaxies over eons. Gaming and cinema aren't alone. In Liu Cixin's The Three-Body Problem trilogy, the attractor becomes a metaphor for cosmic indifference, a force so immense it renders human struggles meaningless. This nihilistic twist contrasts sharply with real astronomy's view, where the attractor isn't a destiny but a waypoint in our galaxy's billion-year journey. What these fictions share is a hunger for cosmic stakes, often sacrificing accuracy for drama. The real attractor won't swallow starships or hide alien armadas. It's a slow, patient force, sculpting galaxies with the subtlety of a glacier. Yet in blending myth and math, these stories reveal something profound. Humanity's instinct to personify the unknowable, to turn a gravitational fluctuation into a character with motives. The truth that we're all just riding the universe's currents might lack Hollywood's flair, but it's a plot twist no screenwriter could imagine. An epic where the hero isn't a starship captain, but a galaxy learning to navigate the dark. For centuries, the Great Attractor's deepest secrets have lurked behind an impenetrable curtain, the zone of avoidance where our galaxy's thick dust and stars blot out the view. But that's about to change. Perched a million miles from Earth, the James Webb Space Telescope is rewriting the rules of cosmic observation, its infrared gaze slicing through the Milky Way's dusty veil like a surgeon's laser. Unlike Hubble, which sees primarily visible light easily scattered by dust, JWST detects longer infrared wavelengths that pass unobstructed, revealing previously hidden galaxies in the attractor's realm with 10 times the clarity. Early test observations already hint at surprises, strange galactic alignments behind the Milky Way's bulge and peculiar star-forming regions that don't match models. But the real revolution begins with dedicated deep field campaigns targeting the zone's core, where JWST will stare for weeks at a patch of sky no larger than a grain of sand held at arm's length, uncovering thousands of galaxies per frame that have never been seen by human eyes. The magic lies in JWST's unprecedented sensitivity. Its 18 hexagonal mirrors collect 6 times more light than Hubble, while its mid-infrared instrument MIRI can detect the heat signatures of galaxies so ancient their stars formed when the universe was just 5% of its current age. This matters because the Great Attractor's origins trace back to these primordial eras, its seeds planted by density fluctuations in the infant cosmos. By studying galaxies at varying distances behind the attractor, JWST will map how its gravitational influence has evolved over cosmic time. Imagine reconstructing a hurricane's path by analyzing layers of sediment. JWST multi-wavelength data will reveal similar stratigraphy in the attractor's growth, showing whether it formed through steady accumulation or violent mergers. Yet JWST won't work alone. Slated for launch in 2027, NASA's Nancy Grace Roman Space Telescope brings a superpower JWST lacks: sheer observational speed. While JWST deep fields painstakingly gather photons from infinitesimal patches of sky, Roman will conduct wide-area surveys 100 times faster, mapping the entire zone of avoidance in months rather than decades. Its wide-field instrument will measure precise distances to millions of galaxies using a technique called spectrophotometry, splitting each galaxy's light into rainbow-like spectra to gauge redshift more accurately than ever. This will expose subtle distortions in galactic motions caused by the attractor's dark matter halo, much like tracking leaves in a river reveals hidden currents. Together, these telescopes tackle complementary mysteries. JWST might spot dwarf galaxies orbiting the attractor's core, a dark matter-rich satellites that could explain its gravity surplus. Roman, meanwhile, could reveal whether the attractor connects to larger structures like the Vela Supercluster through faint galactic bridges. Most tantalizing is their potential to solve the missing baryon problem. Current estimates suggest the attractor contains only half the normal matter its gravity implies. Some theorists posit the remainder exists as diffuse hot gas between galaxies, detectable only via X-rays and subtle distortions in the cosmic microwave background. JWST and IR-SPEC can hunt for this warm intergalactic medium by analyzing how its light filters through galactic halos, while Roman's rapid mapping will determine if this gas clusters near the attractor's gravitational wells. But the greatest revelation may come from an unexpected quarter-stellar archaeology. As Roman scans the zone of avoidance, it will capture individual stars from Milky Way's far side, some of which might be intergalactic interlopers ejected during past mergers with the attractor's satellite galaxies. Their chemical compositions, measured by JWST exquisite spectrometers, could preserve a record of the attractor's growth, much like tree rings encode climate history. Stars rich in alpha elements like oxygen and magnesium likely formed during violent galactic collisions, while those with peculiar orbits might be refugees from galaxies already consumed. The irony is delicious. After decades of theorizing about the attractor's hidden mass, the breakthrough might come not from mapping its present, but from decoding fossils of its past. As these telescopes peel back layer after layer of cosmic history, they're not just illuminating a single anomaly, they're rewriting the story of how all large-scale structures emerge, evolve, and shape the universe around them. And somewhere in that data stream, between the spectral lines of 1 billion galaxies, lies the answer to why our little corner of space is hurtling toward the unknown at 14 million miles per hour. The attractor's days in the shadows are numbered. What if the Great Attractor isn't just pulling us, but pulling from us? Some theorists propose its irresistible gravity might not originate in our universe at all. This radical idea stems from brain cosmology, a mind-bending framework where our three-dimensional reality floats like a sheet of paper within a higher dimensional space called the bulk. Imagine living on the surface of a pond, unaware of the depths below, until ripples from another object brushing the water distort your world. In this model, the attractor's anomalous pull could be the gravitational echo of a parallel universe brushing against ours, its mass tugging through dimensions we can't perceive. The mathematics behind this gets wild. According to string theory, our universe might be one of many brains, short for membranes, existing in an 11-dimensional arena. Normally, particles like photons are glued to their home brain like ink trapped on paper. But gravity, the theory suggests, could bleed between brains, meaning the attractor's extra gravitational kick might come from a neighboring universe's mass bleeding into ours. Picture two bedsheets hanging parallel. Place a bowling ball on one, and the other sheet would dip slightly where the weight presses closest. We'd perceive that dip as unexplained gravity without seeing the source. Critics argue this is speculative at best, a cosmic Hail Mary to explain anomalies that might have mundane causes. Yet intriguingly, certain properties of the attractor align with brain cosmology predictions. Its gravity appears strongest in a specific direction, as if focused along a brain collision axis. Some models even suggest such inter-universe interactions could create cold spots in the cosmic microwave background, like the mysterious cold spot we've observed aligned with the attractor's pull. The timing fits too. If a neighboring brain passed close to ours during cosmic inflation, the gravitational wrinkles left behind could have seeded structures like the attractor. But how would we test such an extravagant idea? The key might lie in gravity waves. Just as ripples prove a pond's surface tension, certain gravitational wave signatures could betray higher dimensional leaks. Future detectors like the Laser Interferometer Space Antenna LISA may spot anomalies, waves that attenuate oddly or arrive from impossible angles. Another clue could come from dark flow, those galaxies moving inexplicably fast toward the attractor. If their trajectories trace back to a single point beyond our cosmic horizon, it might mark where another brain's gravity breaches ours. The most humbling prospect, if true, the Great Attractor might not be an object at all, just a shadow, a cosmic sleight of hand where what we perceive as a local anomaly is actually the fingerprint of an entire other universe, forever hidden from our view but forever tugging at our skies. Whether fantasy or physics, one thing's certain: the attractor continues to defy easy explanation, reminding us that the universe's greatest mysteries might not be in the darkness we see, but in the dimensions we don't. The Great Attractor's gravitational dominion may seem eternal, but the universe has a way of dismantling even its grandest structures. Fast forward trillions of years, and the fate of this cosmic colossus hinges on a silent, invisible force, dark energy, whose gentle push today could become an unstoppable demolition crew tomorrow. Currently, the attractor's gravity binds galaxies together in a sprawling web, but dark energy's accelerating expansion is already stretching the threads of that web taut. Picture a spider's silk caught in a rising wind. For now, the strands hold, but as the breeze strengthens, even the sturdiest fibers will snap. This cosmic tug-of-war plays out in two possible endgames. In the first scenario, the Big Rip, dark energy grows so dominant that it overwhelms gravity entirely, shredding the universe's large-scale structures layer by layer. First, galaxy clusters like the attractor's core would lose their outer galaxies, flung beyond each other's gravitational reach. Next, individual galaxies would unravel, their stars ripped away like petals in a hurricane. Finally, even stars and planets would disintegrate as the accelerating expansion tears apart atomic bonds themselves. The attractor's fate reduced to a diffuse cloud of lonely particles, each hurtling into an ever-darkening void. Yet there's a slower, colder alternative: heat death. Here, dark energy's expansion remains steady, allowing bound structures to persist, but only as isolated islands in an ever-growing emptiness. The attractor's galaxies wouldn't be torn apart, but they'd become prisoners of their own gravity, cut off from the rest of the universe as the space between them and other superclusters expands faster than light can cross it. Star formation would cease as gas supplies dwindle, leaving the attractor's core a graveyard of aging red dwarfs and black holes, their faint glow the only evidence of what was once a vibrant hub. Over unimaginable eons, even those remnants would evaporate via Hawking radiation, leaving nothing but a silent, static sea of photons too stretched to carry warmth or information. The deciding factor, dark energy's mysterious equation of state, a measure of how its density changes over time. If it strengthens, the big rip becomes inevitable. If it remains constant, heat death awaits. Current observations from supernova and baryon acoustic oscillations suggest dark energy behaves like Einstein's cosmological constant, unchanging and steady. But even slight deviations could tilt the scales. Some modified gravity theories propose that dark energy might someday decay, allowing gravity to regain dominance. In that scenario, the attractor could continue growing, merging with other superclusters to form a single, monstrous megastructure, a last bastion of matter in an otherwise empty cosmos. What makes these projections so haunting is the timescale involved. The attractor has existed for barely a third of the universe's current age, yet its demise, whether by rip or isolation, won't occur until the cosmos is thousands of times older. Our entire galactic journey toward it is but a fleeting moment in this epic timeline, and yet these distant fates shape how we understand the attractor's place in the cosmic hierarchy today. It's not just a gravitational anchor, it's a test case for the universe's ultimate trajectory, a laboratory where dark energy and gravity wage their slow-motion war. Even now, subtle signs of this struggle are visible. Surveys of the attractor's outer filaments show galaxies at the edge of its influence clinging weakly, their velocities barely sufficient to resist the growing expansion. Like climbers clinging to a rope fraying strand by strand, these galaxies mark the frontier where cosmic forces vie for dominance. Future telescopes like the European Extremely Large Telescope could measure this delicate balance with unprecedented precision, watching for the moment when the attractor's gravity loses its grip entirely, a preview of the far future playing out in real time. The irony is profound. The Great Attractor, a force powerful enough to bend the paths of galaxies, is itself subject to deeper, more impersonal laws, a puppet on the strings of dark energy's inexorable pull. Whether it ends with a violent tear or a slow fade, its story reminds us that the universe's architecture is never permanent. Every cluster, every filament, every galaxy is a temporary arrangement in an ever-changing cosmic dance, one where the music someday will stop. For all the dizzying scales, we've explored galaxies racing at millions of miles per hour, filaments stretching billions of light years. There's one revelation that puts everything into perspective. The Great Attractor isn't just a distant anomaly. It's our home, or more precisely, our home is part of its home. The Milky Way doesn't merely drift toward this gravitational giant. We're embedded in its sprawling supercluster, Laniakea, like a single leaf caught in the currents of a vast river. Picture this: if the cosmos were a metropolis, Laniakea would be the continent-sized megacity we're born into without even realizing it. Its boundaries enclose roughly 100,000 galaxies, all flowing toward the attractor's gravitational basin, an expanse so large it would take a beam of light 500 million years to cross from one end to the other. Yet for all its immensity, Laniakea isn't a shapeless blob. It's a delicate web of galactic tendrils, with the Milky Way perched on a relatively quiet branch, not unlike living in a suburban neighborhood at the edge of a sprawling capital. Zoom out far enough, and our entire local universe reveals itself as an interconnected watershed, where gravity's pull defines the cosmic geography as decisively as mountains and valleys shape Earth's landscape. What's humbling is how recently we grasped this truth. For centuries, humanity's cosmic address stopped at Milky Way. Even after we discovered other galaxies, we saw them as isolated islands adrift in emptiness. Only in 2014, with advanced redshift surveys and supercomputer simulations, did the full map of Laniakea snap into focus. Its name, Hawaiian for immeasurable heaven, captures the awe of that moment, realizing we're not just passing through the attractor's domain, but permanently bound to it, part of a structure so vast its outline defies intuition. Yet this reorientation goes beyond astronomy. Mapping the attractor reshapes something deeper, our existential coordinates. Think of pre-Copernican Earthlings convinced their planet anchored the universe. Today, we know we're orbiting an unremarkable star in an unremarkable galaxy, drifting toward an unremarkable supercluster. But here's the paradox: that very unremarkableness is what makes it extraordinary. The attractor isn't some freakish outlier, it's one of countless gravitational nodes threading the cosmos. And if even a structure this vast is mundane, how much grander must the universe be? There's a quiet poetry to our place in Laniakea's tendrils. We're not at the center nor the edge, but somewhere in between, participants in a slow-motion migration that began before Earth formed and will continue long after it's gone. The stars we see at night aren't just distant suns, they're fellow travelers in this galactic current, all swept toward the same invisible destination. And while we'll never reach the attractor's core, its pull ensures our celestial neighborhood remains in motion, a reminder that even the grandest structures are just waypoints in an unfinished journey. So the next time you look up, remember, you're not just standing on a planet, you're riding a galaxy adrift in a supercluster's tide, caught in a flow that connects you to the largest patterns in existence. The Great Attractor isn't just out there, it's written into the fabric of our cosmic address, a silent partner in the story of where we've been, where we're going, and how impossibly vast the stage really is. From the Great Attractor's hidden mass to the cosmic tug-of-war with the Shapley Supercluster, these 30 revelations have peeled back layers of a mystery that defies simple explanation. We've traversed vast cosmic webs, navigated through voids like the KBC and dipole repeller, and even glimpsed the possibility of unseen dimensions tugging at our universe from beyond. Yet for every answer, like the Norma cluster's role as the attractor's beating heart or dark flow's eerie suggestion of unseen forces, a dozen new questions emerge. The attractor isn't just a destination, it's a mirror reflecting how much we don't know, from the true nature of dark matter to the universe's ultimate fate. Consider the paradox at the core of this journey. We're hurtling toward something we can't fully see, steered by gravity's invisible hand, while the universe expands around us, stretching the very fabric of space. It's a dance of forces playing out over scales so vast, they humble even the grandest human achievements. And yet, here we are, tiny, curious beings on a speck of rock, piecing together clues from frozen sound waves, rogue galaxies, and the faint afterglow of creation itself. Carl Sagan's pale blue dot perspective rings truer than ever. Our quest to unravel the Great Attractor isn't just about mapping a gravitational anomaly. It's a testament to humanity's relentless drive to find our place in the cosmos. Every telescope pointed toward the zone of avoidance, every supercomputer simulating dark matter's tendrils, is part of a story that stretches from Galileo's first glimpse of the Milky Way to JWST infrared eyes piercing cosmic dust. So as we look up at the night sky, let's not just see the stars, let's see the currents carrying them. And to you, the explorer who joined this journey, which revelation left you breathless? Was it the attractor's cannibalistic feasts, the 21-centimeter whispers of hydrogen, or the chilling possibility of a multiverse's gravitational echo? Drop your favorite aha moment in the comments, because the greatest secret of all might be how much we've yet to discover together.